Section 2.9, Amazon Aurora's Benchmarking. In this section, I'll give you insights into Amazon Aurora's performance benchmarking, which includes other major feature-specific benchmarking as well. MySQL Sysbench is a benchmarking suite that allows you to get an impression about system performance on the CPU, file I/O, and MySQL performance under an intensive load. This test was run on 4 client machines with 1,000 connections each, reading from an Amazon Aurora R3 8XL database with 32 cores and 244 gigabytes of RAM, the largest instance type that you can use with Amazon Aurora. They were able to achieve 107,000 writes per second and 585,000 reads per second. It wasn't that long ago that 1,000 reads or writes were good, so these are super awesome results. Benchmarking in a lab setting doesn't actually replicate a real-world setting, as we all know, so you yourself can reproduce these results. The first step would be to create an Amazon VPC or use an existing one. Then create 4 EC2 R3 8XL client instances to run the Sysbench client. All 4 should be in the same availability zone. Then enable enhanced networking on your clients. Then tune your Linux settings. See the white paper in the link on the bottom left of the screen. This will actually walk you through the entire benchmarking steps, including the steps outlined here. Then install Sysbench version 0.5. Then launch an R3 8XL Amazon Aurora database instance in the same VPC as your clients. And then start your benchmark. The results will be reported to the command line. Following the setup on the link to the PDF on the screen are the best practices to follow to get the same type of numbers on your own Amazon Aurora database. In a real world, you have to deal with multiple users making multiple requests, so requests contend with each other that decreases performance. Quite often, there are situations where the metadata doesn't fit in the data dictionary cache, and it would overflow, leading to poor performance. And also quite often, the data rarely fits in the buffer cache, so data overflows. And in the real world, you don't want your databases to go down. You want high availability and fault tolerance, meaning you'll have read replicas and failover and things like that. So the Aurora team ran some real-world tests. The first test I'll talk about is scaling user connections to test contending requests. They use Sysbench OLTP workload with 250 tables. They scaled connections seen in the first column from 50 to 5,000 connections. Looking at the second column, you'll see that Aurora scaled with the amount of connections, and its performance actually improved. And looking at the third column, for Amazon RDS for MySQL, its performance degraded. And this was one heavy-duty MySQL instance with 30,000 provisioned IOPS in a single availability zone, which is the biggest box you can get for Amazon RDS MySQL. Aurora was able to perform up to 8 times faster. The next test was about the data dictionary cache. So they scaled table count and ran from 10 tables to 10,000 tables, and they compared the throughput. They ran it against 3 flavors of MySQL in Amazon RDS. The first one was again the RDS MySQL with 30,000 provisioned IOPS, just like the instance run in the previous test, seen in the last column. The second one, in the fourth column, was running on an i2 instance using RAM disk. i2 8XL instances are super great instances running on EC2. The third one, in the third column, which was run on an i2 instance, which has great I/O to its local SSD instance store. And in all of these cases, Amazon Aurora ran up to 11 times faster. What this really shows is that I/O isn't the only problem here, because for the RAM disk configuration, I/O isn't what's bounding performance. It's internal things like lock sharding and algorithms that are happening internal to the database tier that's causing the performance not to scale. The next experiment tested what if your data is bigger than your buffer cache. They started with a gigabyte dataset, which would fit in most commercial caches available, but then they scaled it up to a terabyte. Amazon Aurora's performance went down. It was stable up to 101,000 writes. Then it went down about 4 times. But if you look at what happened to the RDS MySQL instance, its performance dropped significantly more and much earlier than for Aurora. The final result was that Aurora performed up to 67 times faster in this case. To confirm these results, they ran the same experiment against Cloud Harmony TPC-C benchmarking, which calculates throughput numbers, and in this test, Aurora was running 136 times faster. The next experiment ran in a highly available, fault-tolerant mode, which translates to running read replicas. In the case of RDS MySQL, you can do up to 5 read replicas. Running that, you can see in the third column that the replica lag goes from a few milliseconds when doing 1,000 updates per second to over 300 seconds when it's scaled to 10,000 updates per second. That's a lot of lag for replicas. And this means if you fail over to a replica, you will lose a ton of data. Looking at Amazon Aurora's results in the middle column, as you scale from 1,000 updates to 10,000, the replica lag is quite constant, reaching a little over 5 milliseconds, which is a great lag number to have for failovers. So in this case, Aurora was performing up to 500 times better than a similarly powered MySQL instance. You might be wondering, how are these amazing results achieved? If you want to scale your database performance, there are some things that any commercial database does, such as lock sharding or improving algorithms on the database tier. But you need to do more than that. It's not architecture at this point. You have to either do less work or do work more efficiently. To scale performance, it's all about I/O. So how you do I/Os and how many you do impacts performance greatly. When you're talking about network-attached storage in a distributed system, it's all about how many packets per second, and you need to minimize the amount. Now you can do 1 million to 2 million packets per second on a high-end hardware device like EC2 with network-attached storage, but at a certain point it won't scale. And you can't really afford to have context switches, which makes performance go down. So you can see that a lot of what the Aurora team did to get these results was to reduce the number of I/Os, reducing the number of packets you're driving to storage, and moving toward asynchronous processing. You remember Jeff Barr's blog from video chapter 1.0, right? Well, here he is with his awesome smiling face. If you don't remember, Jeff is Chief Evangelist at Amazon Web Services, and he has this great blog where he miraculously keeps everyone abreast of the number of changes and frequent changes made in AWS. I encourage you to visit his blog often. Jeff's blog URL is at the bottom left of this slide. With the frequent updates to Amazon Aurora, I'll add them as they are released during the process of making these videos. This recent blog post URL is on the bottom right of the screen. On October 18th, 2016, Jeff announced 2 new features for Amazon Aurora, both involving working with other AWS services that greatly enhances Aurora's functionalities. Because both of these features involve integrating with other AWS services, you must grant Amazon Aurora permission to access the services services described on this slide. The first update is Lambda function invocation. Relational databases use a combination of triggers and stored procedures to enable high-level functionality. Triggers are activated before or after some operations are performed on a particular database table, such as insert, update, and delete. Stored procedure scripts can be run in response to the activation of a trigger. You can now write stored procedures in your Amazon Aurora database that invoke Lambda functions. This allows you to wire your Aurora-based database to other AWS services. Some examples would be that you can send email using Amazon Simple Email Service, or you can issue a notification using Amazon Simple Notification Service, or you can insert publish metrics to Amazon CloudWatch, or you can update an Amazon DynamoDB table, and much, much more. At the application level, you can implement complex ETL jobs and workflows, track and audit actions on database tables, and perform advanced performance monitoring and analytics. The second update is that you can now import data directly from an Amazon S3 bucket into a table in an Amazon Aurora database. Prior to this update, you would have to copy the data into an EC2 instance and import it from there. The data can be located in any AWS region that is accessible from your Amazon Aurora cluster and can be in text or XML format. For more information on how to implement these new functions, or to get links for further information, take note of the URL at the bottom right of the screen, or simply search on Jeff's blog. Quiz time for Section 2.9, Amazon Aurora's benchmarking. Question: which statement below best summarizes how Amazon Aurora's amazing performance is achieved? A. The Aurora team architected Amazon Aurora to achieve 107,000 writes per second and 585,000 reads per second. B. The Aurora team architected Amazon Aurora to achieve a higher number of network packets per second without affecting performance. C. The Aurora team architected Amazon Aurora to do less work more efficiently. D. The Aurora team architected Amazon Aurora so that all data fits in both the data dictionary and buffer cache. Answer: C. The Aurora team architected Amazon Aurora to do less work more efficiently. Explanation: in essence, the Amazon Aurora team reduced I/O in as many places as possible and reduced the number of network packets per second and made everything asynchronous to provide incredible, predictable performance. This concludes Section 2.9, Amazon Aurora's benchmarking. Coming up next is the last section of 2.0, Section 2.10, Understanding Amazon Aurora's Security Architecture.